Okay, we are going to follow a distinguished panel session. And I want to introduce Dr. Harsha Honnappa, Associate Professor of Edwardson School of Industrial Engineering, who will moderate the distinguished panel. Dr. Honnappa?
Thank you, Son. So thank you all for being here. And first of all, thank you to the panelists for agreeing to be on the panel. Besides Martin, you had no choice. So let me briefly introduce the panel. You know Martin Wainwright, of course. David Inouye is in the School of Electrical and Computer Engineering, assistant professor. Ana Maria Estrada Gomez is an assistant professor in the School of Industrial Engineering. Guang Lin is the Associate Dean of Research and Innovation and the Moses Cobb Stevens Professor in Mathematical Sciences and Professor of Mechanical Engineering. And finally, Mohit Tawar Malani is Executive Associate Dean of Strategy, Research and Innovation and the Allison and Nancy Schleicher Chair in the Daniels School of Business. And just to give you a bit of context for this panel, when Son asked me, and based on what Martin was going to talk about, I felt like maybe we could expand the scope a little bit, the lens, and ask ourselves, what's the role of generative AI in data analysis, data sciences, and decision making? And when you think about it, it's kind of an interesting time to be asking these questions because we are, 3 years into the ChatGPT era? And almost a decade into the Transformer and GPT era. So it's a good time to pause and ask ourselves where we are right now, but also, if we take a critical lens, then where are we going? What should we be doing? So with that introduction, let me start with the first question, and this is directed to Guang Lin and then Ana Maria. This is about, thinking about hallucinations in LLMs, and can we use them as scientific hypotheses? And so, for instance, when you think about drug discovery and material science, you can use these hallucinations as candidate hypotheses that you test in the lab. So what kind of validation pipelines, like filters, priors, experiments, or field trials are necessary to make these types of hypotheses scientifically and operationally credible? So, Guang.
Okay. So first of all, I think it's a very good question, right? So if you're just using LLM to predict which thing I'm going to buy at Amazon, right, or which video I'm going to watch at YouTube, it doesn't matter too much, right? If it's a 10% error or 20% error, it's still acceptable, right? But if you want to, like in this Armstrong building, right, you want using LLM to predict what's the success rate for this aerospace shuttle design, right? I think that become a critical problem. So during my PhD, so my training is on study so-called uncertainty quantification and like verification and validation. So I work with like San Diego National Lab on kind of on this critical like a nuclear plant planning, right? All these kind of things. That is critical, right? You cannot afford very large errors, right? So that's what I'm thinking. We can using that technology to apply to develop its so-called multi-layer validation architectures. If you think about like in the Sandia, they try to design as an aircraft, right? In aircraft, there's so many components, right? So there's from like a very single component level to the subsystem level to system level, right? In each level, you have to do a verification validation. You probably the uncertainty from each level going up, right, in the design space, in the simulation space, right? I think all that we should adapt that to the LLM design. So that's why I think we should develop a hierarchical design. First of all, think about when we're training our large language model, right, we should add physical constraints, right, like a so-called physical informed, right? You add some, because you know the physical law, right, in a lot of sense, you should include that, right? And then you know the symmetry of the data, right? You should consider to make sure it is symmetry, guaranteed. And also, you know some invariant, such as mass conservation, momentum conservation, energy conservation, right? You should use that, right? Because you should add into your constraint of your loss function when you're training your large language model, because that will guarantee you satisfy the physical law, right? I think that's the first layer, relatively cheap, help you to constrain that. On the second layer, we should, once you discover something, right, you should go back to run your simulations, right? If we are good at finding element or some other simulation model, you should use that to validate it, right? Another thing I'm working on something like material discovery, right? Well, I can use AI to discover a lot of kind of novel structures that was supposed to give me the best performance, but I have to check. I have to run DFT simulations, right? To ensure that DFT can give me the same thing, right? Have to pass all these checks. On the last layer, we have to go through experimental validation too, right? You have to go to the lab and do the experimentation to make sure in the lab space also validate, right? I think this is a hierarchical, this is validation. I think it's very important.
Yeah. Great. Thank you. Anna?
Yeah, so, well, when I was thinking how to use generative AI for decision making, I was thinking the first thing would be awareness, because I think people who deal with data knows that the outputs are not 100% certain. But people who don't know how these models work behind the scenes, they see the answer and they think, oh, this is true. And I've seen it on students who came and said, oh, you made a mistake grading my homework because ChatGPT said that this is the right answer, right? So they don't even understand that ChatGPT makes mistakes, right? So I think the first thing is when we go out and talk to people that are not technical, explaining them that that's just an output from a model and it might be a hallucination, and kind of train them on being smart about this output. I think that's the first thing. Then, I guess, more technical things. First, I think it'll be good to figure out a way of getting some sort of uncertainty quantification from these answers. Because if we knew that, okay, the model is 99% confident, then we might be okay with making a decision based on that. But even it might be field dependent, right? Maybe precision medicine, they won't be happy with 99% confident, but then AlphaGo or any problem where you can have 10%, 20% mistakes and like nothing would happen, then that's okay. So some sort of uncertainty quantification, I think that'll be nice. Then the other thing is, if we want to treat this as hypothesis, then I still think a human in the loop would be useful, so that we can have many, like, let's say, options, and then the human in the loop can reduce that number and say, well, these just, they don't make sense. Why? Because I know, right? I have the domain expertise to say, like, this does not make sense. And then the other thing, thinking about the data hungriness, I think this could be used, like, we could build methods to decide which of these hypotheses are worth testing first. So that we can use our resources smartly.
There's some kind of ranking and selection of hypotheses.
Yes, some sort of kind of adaptive learning, right? So I decide which of these hypotheses are better, I test them, and somehow feed them again to the model so that it eventually learns from experts or from people actually running the experiments.
Great. Yeah, so building on this idea of hypotheses, well, hallucinations as hypotheses, this is a question to Martin and then Mohit. You see lots of situations where LLMs are used to propose experiments that are then used in field tests. So the model proposes, and you do either a lab experiment or you do like an A/B test, and then the results are fed back in some way. So where do you see this loop working in practice, in science and business and in engineering? And what are the main bottlenecks in terms of data quality, experimental throughput, or organizational willingness to use AI for these types of purposes? Martin?
Sorry, is my mic on?
Yeah.
Impressive. Not AI, natural intelligence. Yes, so several parts to the question. One certainly sees this working in many domains. As you mentioned, A/B testing in like tech companies, this is being done all the time, that you're sort of proposing things that then can be rapidly tested and sort of iterate through design space quite quickly. Certainly the case in material design, drug discovery, physics as well. So we definitely have cases where this is happening. I think cautionary messages or things to be careful about. You mentioned, one has to validate these things. Validation could mean running an experiment. Experiments take time, they take money. You were mentioning sort of more clever adaptive learning. I think one wants to be quite careful in the way that you use LMs so that you don't end up chasing down hallucinations, wasting experimental time and money. I think this is actually also, it's important to think about that any validation that we do is statistical in nature. You mentioned this, it's based on data. Data is noisy. As a statistician, we all know that the more questions you ask data, the more likely it is to lie to you. So if you're using an LLM to explore space, asking many questions, you're going to have to be quite careful in accounting for the fact that data reuse and correction, things like that. On the organizational point of view, I think it's also interesting. I guess I worry a little bit about LLMs would allow us to search design spaces very quickly. It could allow us to sort of find near optimal things quickly, but I worry about the risks of over-optimizing. If you sort of fix one objective and optimize it, often you're sacrificing other things. So I could design systems that are very fast but are fragile and unstable. I like to think of the world in a more sort of multi-objective setting. So I think we need to be a little cautious, just not naively using LLMs as black box sort of optimization procedures.
Mohit?
Hypothesis testing, and particularly A/B testing and other things, as Martin and others have mentioned, companies are using them for trying to think about how they can redesign what they can show people and things of that nature. Probably not as costly in those type of settings. In other types of settings where this is sort of, we know that people are trying to use this as molecular design, material design, drug discovery, and so on and so forth. I think the second part of the question dealt with challenges, and I think there are more challenges than we can count just sitting here. But many of them are around the first question that you talked about, which was hallucinations for sure. I think the key question that, at least from my perspective, I think about is the problem of generating answers is a different one than verifying answers. Yeah. And to me, the notions, at least in optimization theory and other places, we've always distinguished these two tasks quite a bit. And I think that comes to fore here because you have a solution that has been proposed, and now you're trying to verify whether that solution is good or not. And so you can go do an A/B testing, or you can do a more mathematically rigorous way of sort of verifying some of these things. Those tools are still in development. I think to a lot of extent, we have been more focused on the search problem rather than the question of verifying an answer that was given to us. That poses some new questions for us to sort of worry about. How can we know that this may be wrong, or how can we sort of then do things to modify it? So with that said, the hypothesis testing brings in other questions like data quality that you mentioned. There's a lot of data needed in order to generate good hypotheses. If this is a setting where we don't have such kind of data, I don't think there's a very legitimate possibility to use LLMs in those setups. Once you have sort of got your experiment in place, I think there are also a lot of issues related to people accepting this in an organizational sense. So there's a trust issue with many of these things. People who are knowledgeable do understand that these mechanisms or the outputs are often erroneous. The problem is very close to what we call prompt engineering. When we raise prompts and we get an answer, we are always trying to verify whether this answer is correct or not. So this is the fundamental problem, I think, at the heart of whether these mechanisms are useful, and people are not very trusting of these. There is the question of whether it takes away people's jobs. I think there are many questions related to this, and people are worried about those issues as well. So organizations are not willing to accept them. There are good reasons for not accepting them, but then there are also reasons which are not necessarily just related to the mathematics of it or the reasons that are sort of in theory.
Yeah, excellent. Yeah, so even if we think about, you said you need lots of data to validate these things, but even if you train these models, these foundational models with lots of data, they can be subject to problems like distribution shift that you mentioned. And so this is a question directed to David and then Martin. This is around simulation and the robustness to distribution shift. So, once you deploy the model in the field, the world changes. And, if you're drawing strong conclusions from these models and the world changes, then that's a bad thing. With today's tools, how far can we trust these simulators or these models to generalize to out-of-distribution regimes? And maybe you can comment on rare event estimation as well, if possible, rather than just memorizing past behavior. So what might be the promises and pitfalls of using generative AI for this type of method?
Yeah, so for the first question about trust, I think this is kind of a funny word. I think we need trust, mental models for trust for AI. Like we have an understanding of how much you should trust a person. We have understandings of how you should trust a book. We have some level of, it's like, we've had these for a long time, so we kind of understand how to associate trust. I think AI is this new thing in which we don't have a good understanding of how do you assign, what's the right kind of trust, both the quality and the amount. It's not just like a spectrum, but you trust, you trust certain people who are experts in the area, they trust them for that, but not necessarily for other things. So I think in terms of whether you trust the predictions is a bit of a hairy question because in some senses the answer is definitely not, but then so maybe I'll answer kind of more broadly this, the good, the mixed, and the bad, in my opinion. So the good, I do think there's this ability to set up simulations with natural language that just would have been either too costly to set up before, because now you can write a huge meta prompt to simulate a scenario and help it reason about that. And I think that has, it might be helpful for, say, a CEO to do this, or for a technical team to design a prompt and help it think through things. So that's possibly where I think simulations could be useful for complex scenarios in certain ways, because you can set it up with natural language. And the mixed bag is that I think these reflect human intelligence in some way. They're trained on things that humans wrote. So they have both the good qualities of human thinking and the bad qualities of human thinking. So it's not that all humans think all really clearly and well. So I think there's a little bit of an issue there on a fundamental level. And the bad, of course, is the spurious correlation type of issue where there's changes when the environment changes, when there's an intervention on the system in some way, when you change something about the environment, correlations could change in ways that you don't understand. If they're not causal, if they're not kind of fundamental, then they could even reverse. So things like panic buying, for example, when something's low, the demand goes up higher when they're scared it's going to run out. And so the effects that you would see in one case are either going to be reversed or highly changed in a new scenario. So when these novel scenarios you're talking about are rare events, those are inherently things we haven't seen much data on. We have a very, very small amount of data on the rare events. And the fundamental dynamics of the system might have correlations that are very different than what we had before, and that'll cause these things to fail, I think, in surprising ways. They don't fail in the same way that our physics simulators fail. Physics simulators aren't perfect, but they fail in ways that we kind of understand. These are going to fail in ways that we didn't expect, and so that could lead to some bigger issues.
Yeah. Martin?
Yeah, so I guess there are, again, multiple parts. So maybe talking first about the utility of simulators. I think if we broaden the scope a little bit away from just language and sort of think, what can transformers do? Really sort of transformers are very good at predicting sequences. They're really taking, Shannon suggested that one can generate language by building Markov chains on sequences of characters or words, and he did that, well over 50 years ago. Yeah. So really, transformers are just an instantiation of Shannon's idea, but with much richer, longer context predictive models. In terms of simulation, I think the ability to build good sequential predictors is useful much more broadly than just language. Language is one thing that's sequential, but there are many phenomena that are sequential where I think more broadly transformers, and I think we mentioned state space models, things like that are going to have impact moving forward. I guess the second thing maybe to highlight, you sort of mentioned distribution shift, and you were sort of mentioning these issues as well. I think it's very important that we think carefully about it. It is a major issue, and it is, I think, hidden in a lot of sort of the popularization of deep learning and so on. Yeah. I think the most extreme example, the thing that blew my mind, was in 2017, Ben Recht and some of his students and postdocs, he was a former colleague at Berkeley, did the following experiment. They tried to replicate the ImageNet. ImageNet was a big database of images for classification. So they said, let's make a new copy of it. And they were very careful and systematic to try and reproduce as carefully as possible something that was like, another version of ImageNet. But yet, despite their care, they found that classifiers' performances dropped by, 10 or 15%, which is major, like a major drop. And it turns out to be due to very minor differences. Again, JPEG is your friend. There was a different version of JPEG in the two generation processes being used. But it's a very extreme example of, you want something that is predicting semantically useful things like image classes. It should be strongly robust to things that have nothing to do with, image labels. And we're not at that point. That's an extreme example, a little cherry-picked, but it's generally true. So I think we need to tackle this. And Guan, you mentioned sort of the idea of building in, physics, like possible invariances, symmetries, things like that. I think we need to move a little away from like purely data-driven things and actually combine data-driven with modeling and domain structure and think more carefully. I think that will start to help things like brittleness and distribution shift. So I think that's exciting, and that's being done. People are certainly doing these, particularly in physics and chemistry, materials design. But I think we need more of that more broadly for this issue.
Fantastic. So, this brings me to the second part of this panel discussion, which is what's next. And the first question is to Mohit and then Guang. In terms of improving autoregressive token generation, so as Martin mentioned, these are producing one token after another, and large language models today are essentially next token predictors. But if you think about long horizon scientific simulation and business decision making, for example, or operational planning, what kind of architectural or training changes do we need beyond just predict the next token better? So incorporating maybe the physics, perhaps. Do we need like trajectory level objectives, some kind of hybrid training method, modeling methods? What are your thoughts, Mohit?
Sure. So I think Martin already mentioned one of the primary things that people at least have been attempting to do, which is incorporating model-based insights into the AI architectures. You can think of AI is really producing a variety of building blocks, if you will. There are graph neural networks which are good at certain things. There are transformers that are good at certain things. There are even basic equations that we can backpropagate over. They're differentiable, and so on and so forth. So I think putting those architectures together is a pretty useful thing to do, at least in our experiments with trying to do something in the logistics space. Having real probability convolutions and having real equations in the middle of these AI architectures helps them perform much better than in the absence of these things. So if you throw just a deep neural net, it's very brittle. You change things a little bit on it, and the predictions go pretty haywire. So I think that's a useful thing. Mm-hmm. But the question, as Harsha posed, I think was quite broad in the sense that errors accumulate. So transformers are great at predicting the next they're autoregressive in some sense. And so the idea of predicting some 10 words down or global information is sort of lost. Now, in that regard as well, there are these new systems that are coming into play where if you're trying to produce a mathematical proof, then maybe trying to check the next logical step and it's correct is actually a good thing, because there are proof-based systems that can check and verify at every stage, so you are in the correct space. So systems like Lean and others, which are being used for developing mathematical proofs, are one such possibility in that direction. But I think the difficulty is when you talk about business decision making, I think that's a little bit more complex than we are dealing with right now. In fact, if you've heard of this Project Vend by Anthropic, which was essentially to produce a run on Claude and a vending machine which was only open to Anthropic employees. And they could ask for anything to be restocked and so on and so forth. And that's a very nice story to sort of look at it gives you a sense of how far we are. So just for the vending machine, it started to order tungsten cubes because somebody said, I want a tungsten cube. It did not leverage opportunities. Somebody said, I'm willing to pay you $100 for this, which could be procured with $10 to $15. It said, I will take that into consideration, but never actually did it. Yeah. So, I mean, if you start talking about business decision making, there is customers, there is interactions, there is all sorts of things going on. I think structured problems is where I would first try to solve, rather than sort of saying long-term autonomous decision making. I think we are far away from that place as of now. So.
Okay. Go on.
Yeah, so if you look at the history, right? So if you look at Gemini, ChatGPT, right? All these tools, right? So this is a very competitive field, right? So all the models are auto-regressive model, right? And the model become bigger and bigger. They somehow goes to like billions and billions of parameters. So that makes the field very competitive. So basically, if you don't have thousands of GPU, you're out, right? So that means academic is out. Right? We have no chance because we don't have the money to buy all these GPUs, right? So that make it, I think, where's our chance, right? I think, so that means we have to try other architectures, other approaches, right? So one example in my recent work, we have one iClear paper. So that is, we developed using different architecture. This is a so-called, we call DD instruct. The idea is using the mask, the discrete diffusion model instead. We're using that to generate text. So that can beat like ChatGPT 2 64 times faster. So the reason is because auto-regressive model is like a serial machine. So every time I think you have experience when you talk to ChatGPT, right? You can ask a hard question that they're going to generate a text very slowly. They say, oh, you go get a coffee, come back, I will finish this task, right? The reason is because it's a serial. It's one token by one token is the generation. But however, the discrete diffusion model give you it's like, think about it's like parallel machines, right? Yeah. It can parallel generate. So that's why it's intrinsic is faster. Okay, so that's what I'm saying. It's one possible way. So in my thinking is in the future, it's not just still not just the discrete diffusion model. It has to be hybrid model, right? It also has to be like you have to use mixed precisions, and for the training. Also depends on what you want to do, right? You think about we are engineers, right? If you want to do the edge computing, you want to edge AI, you want to have very cheap sensors with the intelligence. You cannot have luxury install Gemini inside it, right? You just don't have the power even, right? So that's why you need to have some light-weighted, LLM to be installed. Also think about the cell phone, right? So think about you are in a rural area with your cell phone, you don't have signal, right? You want to have some AI model installed there can help you, make decisions, right? All these examples It's not like one big model solve all the problem, right? You need to have some lightweighted large language model to help you on that aspect, right? So yeah, that's my thinking.
Thank you. So, building on this question, so this is directed to Martin and then David. What do you see as a post-transformer architecture for, if you think about world models now, expanding, the possible type of, AIs that we can think about? Martin?
Well, I guess to start, I wouldn't say post-transformer. I don't think transformers are here to stay. I think it was described, I forget, one of you said, sort of, the right notion is sort of we have different modules. We have many different kinds of modules, and they excel in different regimes, and we can sort of plug and play. I do think some of the newer sort of state space models, things like Mamba and so on, are interesting because they're an instance where instead of being purely data-driven, you're actually trying to encode in the model, in the architecture itself, some notion of structure, of actual dynamics. Yeah. So I think that's very important. I think in other realms, we mentioned this before, where there's like symmetries or invariances and things like that, also architectures that respect those things are very important. They're actually not trivial to build either. It's actually quite hard to build some of these architectures that respect structure like that. Yeah, so I wouldn't say post-transformer. I would sort of say, I don't know, it's like a zoo. We have like a zoo of different animals, and they can interact, they have different abilities. And I think what's exciting is, well, the challenges we've talked about, something like validating and certifying, but what's exciting is sort of that one can build on these in very interesting ways. You have black boxes that can solve very complex problems now, like sequence prediction problems or image generation problems. This can be done. What can we do with these boxes? That to me is sort of the view moving forward.
Yeah. David?
Yeah, so I kind of would think of the current age as kind of understanding what we've already seen. Like we already have this text data, we already have this video data. Now we figured out how to use it. If you can give me data, I can do something useful with it. Like if you give me quality data. I think if I was to think about broadly what the next age will be is something about reasoning about what we don't see or what we haven't seen yet. And so that's this, I think it's, that includes uncertainty, that includes extrapolation, this out of distribution. How do you handle situations you haven't seen before? Like with the physics simulator, right? You can validate it on, say, 2 balls bouncing around. And it's like, okay, this looks good. This matches reality. And because we've used physics to kind of design this model, we can then extrapolate it to 100 balls. And we can simulate 100 balls. We just need more computation, but we're reasonably confident it would simulate 100 balls, even having just checked 2. I don't think we have that for data-driven models yet. And so I think reasoning about what we don't know is kind of the unseen is going to be the hard part. And I think the only way we can even do that as humans is kind of going to some higher principle usually. Like in a new situation, an entirely new novel situation, we often move up kind of in our reasoning about what decisions we would make and so forth. And the idea of invariance, I really, conceptually I like the idea of incorporating structure. I think I push, my maybe hot take is to kind of say, can we, instead of formulating as mathematical constraints or architectural constraints, is there some kind of data that we can get that encodes those constraints? Because the current age is really based on this, supervised pair, essentially, the XY pair. Everything, as Marian was talking about, everything is really based on this abstraction of an XY pair. And maybe there's another abstraction that kind of gives us a way to model constraints. It's kind of like we have the optimization objective. We don't have a good way of easily describing the constraints we want on a system in the same way like inequality constraints on optimization problems. You have some sort of constraints there. I don't think we have a good way to do that.
So just to clarify, so you're not saying that these are physics-type constraints. So you can have like an equation, for instance. You're saying something else.
Yeah, I'm saying using data to define the constraints you want on the problem. So it's a bit more abstract. So it doesn't have to be a lot of, I feel like in medicine, for example, it's very difficult to write down the equations, but then if you ask the doctor, they can tell you kind of what kind of constraints they think are reasonable. And so I think that would be potentially a more scalable approach ultimately if we can come up with a better data abstraction on how to encode constraints or structure without resorting to enforcing it on an architecture, because that is very hard, I think, to enforce, a type of invariance that's not mathematically easy to write down.
Okay, great. So the next question is directed to Anna Maria and then Martin again. This is about learning and validating with, if you're going to learn and validate tail behavior, right, from thin data. So when you think about systemic failures or catastrophic shocks, you don't see it in data, right? So you just have, it's very sparsely available. So if we use generative models in a sense to just fill in, these tail outcomes, you can either do like conditional sampling or tail-focused, training. Then what kind of assumptions about the data generating process are we implicitly baking in? And what diagnostic stress tests and external benchmarks are necessary so that we can trust these types of predictions? Anna Maria.
Okay, I think it's a really hard problem because we're asking machines to solve problems that we've never seen before, and these machines are trained on data. And so if the data is not there, everything that they can suggest is going to be wrong, right? And I think that's the main issue. And we can try to do conditional simulation, but that's assuming still some sort of model that we have is somehow accurate. And for these very extreme events, very hard, right? So we think of COVID, it took everyone by surprise. No one had seen anything like that, right? And even thinking about how humans reason, right? Like different countries enforce very different rules. And even now, it's really hard to say who did the right thing, right? And so even thinking about kind of how to measure right, even for a machine, is really hard. So I think because it's a hard problem, one thing we can do is kind of same thing. You don't trust one machine or one model. You actually need to have lots of them. And even then, just treat them with a grain of salt when you decide what you're going to do. Again, depending on the application. But if we're talking about real catastrophic events that are going to impact people's life, you need to be very careful.
Okay. Martin?
Yeah, I certainly agree. Extreme care is required. I would say, sort of more fundamentally, there's maybe an opportunity for theorists here in the sense that, if you're trying to predict severely out of distribution or deep tail events, it's just a very hard problem. It's just hard, period. Whether it's easier or harder because you're using, modern AI, which we know is quite susceptible to hallucination, that's sort of an interesting question to think about. But a fundamental question is just for a given setup, what is possible, just information theory, what is in the data, what level of resolution can I give you extremely out of distribution or extremely in the tails? At some level, you can easily construct problems where nothing can give you anything useful. You can construct other problems where, yes, you can, because somehow, I don't know, the data has a certain shape, the distribution sort of naturally melds out into the tails. Yeah. Which problems are we dealing with, and what are the sort of fundamental limits? I think we need more fundamental understanding, but I'm super cautious. I'm tail prediction, extreme event is already dangerous and uncertain, and that plus deep learning, it seems like a toxic recipe to me personally.
Yeah. So that's a question for the future, right? Okay, so we're almost at the end. So I'm going to start with Mohit and ask you to give some final thoughts. So it says one sentence, but we have enough time, so you can take 2 sentences. What is the most important technical or institutional change we need so that generative models genuinely improve decision-making and analysis in your domain rather than just producing more impressive demos?
Rather than?
Producing more impressive demos.
So in the domains that I'm interested in, which is business decision-making, I think we need a lot more domain understanding in those models. And I think that's where the big difference will be made. So that's my one sentence.
Thank you. Guang?
Yeah, so I think to make an AI model to be useful, right, I think we need to make it trustworthy, and also we need to ensure it satisfies the physical law behind it, and also we also need interpretable. Interpretability is very important, and so that make it. Don't want a black box. We want either gray box or white box, right? So that way we can trust. Especially you want to apply into medical domain, financial transaction domain. You really need to build this trust, right? A black model will not be able to give you that trust.
Okay. David?
I would say that robustness to out of distribution by kind of ideally verifiable invariants, things like that. This ability to extrapolate, I think, is still, we're really bad at extrapolation. And I don't think LLMs solve extrapolation. They just hide it under something.
Yeah.
I think trust, very important, but also cost is a big issue. I think, again, these models perform well where there's lots of data, but in many instances, getting that data not easy. There's not a lot of data, and then you cannot trust these models. So.
Yeah. Okay. And final word, Martin?
Maybe this is a broader comment, but I think we as academics need to sort of rediscover our mojo, our raison d'etre. There's some sense, right, like you mentioned, we cannot compete with industry, but that's not the right thing. We're not meant to compete with industry. That's not where our competitive advantage lies. Where does our competitive advantage lie? It lies in longer term, sort of deeply creative thinking that's not driven by shorter term, stock price phenomena, things like that. So as academics, just remember that we do have an advantage over industry. It's sort of intellectual freedom and ability to take on risky, different ideas. I sometimes wonder, we have ended up in deep learning partly because of perhaps winning the hardware lottery, that they happen to be very fast to train on GPUs. But are there other models that are just very different that are also interesting that we're not thinking about? I think we as academics, that's where our opportunity lies, in sort of broader thinking like that. So.
Excellent. So I think that's a very positive note to end on. I want to thank all of the panelists for participating in this. And I think that's it.
Thank you.